Hello, gentle readers. It's May 3rd, 2024. Today in Moment in Motion, what there will be more discussion of the mechanics of motion, the mathematics of the mechanics of motion. So over the past couple talks, what there's been considered are the relevant and enduring definitions, the context, the scope, the history, and the development of what is the theory of mechanics, these kinetics and kinematics, which describe motion according to these laws of motion, Newton's laws or Galileo's laws or Aristotle's laws, Aristotle being sort of the greatest compendium of the ancient and most excellent curated wisdom as survives today. The more ancient Greeks and the various notions of the concepts behind the elementary and the substantial and the essence and the existence of things, moment in motion, geometry is motion. And where we left off was basically a rediscovery or digging up, turning up the ideas that there's vis-motrix, and from this we say that all of Newton's laws kind of follow this way, and vis-viva, the kind of like the active motion vis-a-vis the static in motion, in the dynamics of motion. So the vis-motrix and vis-viva saw it as from a time when after Galileo, 100 years was this, and then that was after the Mertonian school, and that this after the Islamic Enlightenment age and the beginning of the European Enlightenment age, with the Mertonian school, then calculators and the notions of the formulaic approach, and then whether potential or dynamis or dunamis being potential, the energy and the resistance were either fractions or differences. And then it was with regards to that in the mathematical model, or the severe abstraction, as Heilbronn put it in his great entry in the Dictionary of the History of Science, was, and as regards to this mathematical model, how it could be sort of as of either way in terms of what then it pretends to convey. And then we arrive at force equals mass times acceleration as the linear moment, the linear impulse, the classical impulse, and as that is a function of time, because there is no real notion of constant acceleration. Something as it accelerates, the acceleration it so exhibits is as of a quantity of a force that converts from potential energy to kinetic energy in a continuous manner. And so there's a lot that goes on then for the mathematics of the mechanics of motion, what the mathematics needs to bring to make it so that it's well defined and well understood, and that it carries forward how to explain smooth acceleration. And so here this has gotten these various concepts of the stop derivative and the walk integral after the usual integral of a distance, as that all the higher orders of acceleration are its derivatives. And that then with some complements to follow that as of this run derivative and pause integral, or like what are the pieces that add up along the way that help explain that in all the different directions of motion, each is linear at any given time, that objects, for example, in general relativity, follow their world line. They just naturally follow the line, whatever line they're following is their world line. Compared to that, there's always some notion, at least, that objects only orbit each other. That objects in motion stay in motion with respect to all the other objects in orbits. Objects at rest stay in rest as the center of all the other notions of the epicycles, of the orbits, and the orbits around that. That any origin is a rest frame, and any rest frame is an origin. And here we have the frames as the locale, and the space as the global, and then also the notion that we have this Rama and Rama, or space frames and frame spaces, as just a natural complement to the models of these things that then help explain for theories like general relativity, and that also for classical mechanics, how objects move along in their space and their space moves along with them as they go. And that for the linear, that it remains Galilean, that this Lorentzian is Galilean again. It's Galilean Lorentzian, or Lorentzian Galilean. And the Lorentzian and Fitzgeraldian is like this way. And then we have the Lorentzian and Maxwellian, because the behavior of the electrical field is radionic, yet it achieves towards light speed. We have these different notions of the Lorentzian, which basically makes for that in the invariant theory, that anything that satisfies being a Lorentzian is basically a solution for the equations of general relativity. And so when we get to the reasons why that linear and rotational are different at all, it's, well, they just are. And that's why we get into space contraction as a thing, that things in the Galilean carry along themselves with it, whereas things in the rotational just kind of spin around and gain this energy, this active energy, or vis-viva, or their momentum. And that it's as real a thing as can be evidenced classically, and not just in the realm of the cosmological sky survey, or nor necessarily in the world's latest, greatest, largest, highest energy particle collider. So these are the things that have been kind of developing here. And so when there was this discovery of the idea that the vis-motrix has a natural complementary dual in this vis-viva, then that helps to explain the attachment to things like this momentum and pseudomomentum, where for forever, or a long time, it was like, well, momentum is a conserved quantity. Well, that system was open, so the pseudomomentum comes and goes, eventually re-arrives, but it's virtual in that sense as it comes back around, pseudomomentum. And then there's also particularly that this notion of the rotational and the centrifugal, what are these fictitious forces, become instead supplementary to the model. What was hidden is now supplementary, as these various empirical things that are always observed and given their special reasoning in the tribology and these kinds of fields in the engineering, also come back to fit naturally enough in otherwise our perfectly reasonable model of the statistical ensemble and thermodynamics second law, fulfilling the role of entropy in the oldest law, that anything that goes up must come down. That it's in equilibrium, that it's always seeking equilibrium. At the same time, organization is a natural state, and that it also matches up with these newer results in the sky survey that must add up, that rotating frames are essentially independent. So that's kind of what we've arrived at over the past few talks and over the longer discourse. Moment in motion. Super classical, sum of histories, sum of potentials. Which results in severe enough abstraction as that trivially and vacuously, eventually, it's just least. So thinking these things over and pondering them is a neat enough way to arrive at that. Then for that, mathematics needs to bring these bridges, is what Einstein calls it, a bridge, from what he has is of the linear to the centrally symmetric. And that being what connects these otherwise different metrics, different spaces of frames, with regards to that's something that is the way of things. There was a study recently of what was on Einstein's blackboard at the end. What did he leave on his blackboard? And what it was this notion of Einstein's bridge, and he kind of worked it out that according to the gravitational field equations and the tensor and this other tensor eta, so for G and eta or something like that, that it worked out for his bridge that they had the same degrees of freedom, and meaning that they reflected that for those degrees of freedom and degrees of fixedness, and they reflect that otherwise the way they come together, it makes up for the same thing. That's when there was discussion here in the reading from Einstein of Einstein's bridge from Einstein's Out of My Later Years, which is where he carried forward this idea already. And that was, you know, the result is that it makes for that. Also, these other things that were so revealed and discovered in Einstein's Out of My Later Years about the spatial and spacial, and that special relativity is local, and so it doesn't really necessarily exclude the Fitzgeraldian, the Galilean, the Maxwellian, each their own Lorentzian. That's the thing. So then the point is that that's not just for Einstein, Podolsky, and Rosen in condensed matter physics, which is where it lives today. I mean, at that kind of energy, it's like, well, that's all we need to have there, and that's plenty, and shows up. That is actually is so for the classical, it's for for Einstein's attack on Newton. When really, though, what we're looking for is Newton's zero-eth laws. Geometry is motion. So this was last time we left off looking at this early Greek philosophy. So there was some question I wondered about. There's physics, Eudemus, physics fragment. There was a quote from Diogenes, and there's a bunch of argument about Zeno's arguments. Simplicius is pretty well informed. Stobachus. I'll be curious what Eudemus says. 37a 101. He's in a section on Zeno. Zeno's treatise consisted of a series of arguments, each designed to show that the common sense hypothesis that there exist more things than one leads to absurdity. So this is a holism in a sense. I mean, it's kind of like there's naturally bookkeeping. The cosmic clockworks never loses a bean. You know, it's continuum mechanics in this manner. This is conservation law, continuity law, all these things. Later sources say that there are 40 arguments of Zeno in all. There are substantial fragments of 2 of the arguments. Aristotle provides a critical paraphrase of 4 more, and we possess accounts of a further 2, arguments of Zeno. These arguments apart, nothing is known of Zeno's philosophy, if indeed there is anything else to know. Fragments are preserved in Simplicius' commentary on the physics. Simplicius is discussing a passage where Aristotle refers to 2 arguments, the argument that everything is one and argument from dichotomy. So often we might point to Heraclitus as the first sort of proponent of monos dualism. Well, how can it be dualism if it's monism? How can it be monism if it's dualism? It's kind of the point. It's the dialectic and the fuller dialectic that 2 things are one, and one thing can be seen in different ways. And Alexander seems to have taken his opinion that Zeno does away with the one from Eudemus's writings. For in his physics, Eudemus says, "Then does this not exist, although one thing does exist?" That was the puzzle. They report that Zeno said that he would be able to talk about what exists if only someone would explain to him how on earth anything could be one thing. He was puzzled, it seems, because each perceptible item is called many things, but by way of predication by being divisible into parts, whereas points are nothing at all. For he thought that what neither increases when added nor decreases when subtracted was not an existent thing. this is the usual notion that points are not lines and lines are not points, and you cannot make a line of points and you cannot make a point of lines. But then the idea is that, well, mathematics, the way they have it to make a line integral, and it's made out of points or a point set. We have a point set topology. We have all these notions of continuous domains. They have what's called the ordered field. It's the rationals. And then you make the complete ordered field by axiomatizing that it's got the least upper bound property, that there are no gaps left in it. And they axiomatize again that, the distance between 0 and 1 has got measure 1.0. Then also we just build that from line rails, and this was like, well, he might not have had points and lines, but maybe he didn't have infinity either. So if you just take the whole numbers, from 0 to infinity and put them over a number that goes to infinity, you take the limit of that function, and the range of that function, the points in it in 0, 1 they have extent 0, 1, density, completeness, because any one of which is just, completeness is just the property that the least upper bound or supremum of a set exists in the superset that they inhabit together. There's not a gap, and here it's just the next one. It's nice and trivial. And then measure 1.0 is a simple enough length assignment. It's like it's 0 to 1. Its length is 1.0. So given that, then it doesn't take much more at all to then equip mathematics, which is the slightest superclassical notion, that in the continuum limit of this function, which is well established these days, it's called distributions. It lives certainly in the theory of statistical distributions, where it introduces some more things, it introduces some more distinctness results to what are uniqueness results. That's another thing about this whole holistic monism, is like a singularity. Well, the singularity theory and multiplicity theory is just a principal branch of a multiplicity. And then in singularity theory, it's the classical and real and principal part. That's it. So there's much to be said for that. Points and lines and points cannot be divided in the infinitely divisible to be so. But as infinitely divided, that's what they are. And Aristotle well addresses this. People point to Aristotle, and this is funny. I said it the other day. It's like, Thomas and Occam, they're like, we read the book of Aristotle. And the Scotus was like, I read both books of Aristotle and read between the lines. And he's got at least two he's got at least two definitions of continuity. And one is the field, and it's Archimedean, and the other one is Zeno's, or otherwise, Aristotle's continuum. So people they'll read Aristotle and say, Aristotle said the definition of points is they're nothing. It's like Aristotle has said that in a section where that's how he's talking about it. And then another one he talked about the other way. Then as regards to how he put them together, he establishes a brief metaphysics, keeping things consistent. If it were added, Zeno says, this does not do away with the one, and then capitalized, so the whole idea of Platonism is that there's a monism, the monad, a holistic totality, a universe of things, or any, thing, that there's discernibles, that there's an identity. But in order to show that each of the plurality of things possesses a size, and this is also what we call the measure problem. And so that's addressed as from algebraic geometry and how to establish theories of measure, like Lebesgue measure, Riemann measure, Jordan measure. A lot of discussion about that here. Themistius says that Zeno's argument establishes that what exists is one from the fact that it is continuous and indivisible. For if it were divided, he says, it would not, strictly speaking, be one because of the limitless divisibility of bodies. So when we say strictly, sometimes that gets into exactly what it means, loosely and strictly. That you can say, well, like an effective or practical or potential infinity is beyond anything that could ever be reached. Is it an actual infinity? No, or it could be, strictly. Porphyry holds that the argument from a dichotomy comes from Parmenides, who attempted to show by it that what exists is one. So Parmenides is to Heraclitus kind of like Aristotle is to Plato. And I just leave Socrates right out. And after Heraclitus and Parmenides, there's the third guy, but that's in the Eleatics, and that kind of gets into Zeno. And then kind of in the interim, in the mists, there's like Archimedes and that, and all the things of this time which have survived in their fragments. Goes on forever. Either some final magnitudes will remain, which are minimal in atomic and limitless in number, so that the whole thing will be constituted from a minimal item and is limitless in number, or else it will disappear and be dissolved into nothing, and so be constituted from nothing. But these consequences are absurd. Therefore, it will not be divided, but will remain one. Again, since it is everywhere alike, if it is divisible, it will be divisible everywhere alike, not divisible in one place and not in another. Then suppose it to have been divided everywhere. It is clear again that nothing will remain, but that it will disappear. And if it is constituted at all, it will again be constituted from nothing. For if anything remains, it will not yet have been divided everywhere. Thus, from these considerations to it is evident, he says, that what exists will be indivisible and partless in one. Porphyry, Commentary on the Physics, Fragment 135. And so it's framed at least to this suppositive, it's like, if it was like this yet, like so. And this is nice when we enter a world of contemplation where there's no but, only yet. So two things that contradict still kind of each carry their own full ways. They talk past each other first, vis-a-vis when they contradict each other and make it so that only one, not yet the other, maybe so. In this contemplation, they're still each so both ways. In either way, and then what remains is, and it's just the dialectics, with, like Hegel says, you got the thesis, the antithesis, and the synthesis, then is what resolves that, and either includes a wider resolution explaining why it's simply not a binary proposition, or excludes one or the other one of them. It's becomes then that much more smoothly resolved, as otherwise just a usual didactic sort of logic that on the encountering of anything that is contradictory falls off the ridge, or bullies its way through in a sense. This also is called, with regards to the idea of concept carrying, is the bridge of bridges of ponds, or sometimes the bridge results here is called the pont, or the bridge. And so the pons asinorum is like the bridge of ignorance, can never be crossed. And so that's this inductive impasse, is that when there's a deductive result, there's Zeno, and every day he's crossing back and forth across this bridge. And somebody comes along, and he's like, well, Zeno, how do you cross this bridge back and forth? And it's like, do I, or something like that? It's like a joke I heard the other day, and I wish I could recall it better at the moment. It's like someone yells, like, how do I get across this bridge? It's like, well, you're on the other side. It's still at the same time that sound travels at the speed of sound, light travels at the speed of light. Earth tilts. Well, that's getting silly. Yet there's furthermore that the Zeno's bridge is the idea that he takes one step at a time, and they're as small as he can take. He still gets across. So it's infinitely divisible. Yet even a snake gets across. Here I'm kind of stretching for metaphor here. Yet it's just to reflect that the inductive impasse in this, the whole idea of the complementary duals and the meeting in the middle of nowhere, and all these kinds of things, has its resolutions in its analytical deduction to arrive at analytische Brücken, analytical bridges. As Zeno's and Aristotle's work on motion, de motu. But why say more when it is actually found in Zeno's own treatise? For showing that if more things than one exist, the same things are limited and limitless, Zeno writes in the following words: if more things than one exist, yet it is necessary for them to be as many as they are, and neither more nor fewer. So he's just expressing that there's a bookkeeping of sorts, and so that when you have two infinities, you say, well, I can take infinity on one and infinity on the other one, and give and take from either one, and they still stay the same. It's like, well, in a sense, that's so, because it doesn't involve any framing or scaffolding, the telescoping and scaffolding. But in a sense, the bookkeeping is still in effect. And so when it ends up being that these are appreciable with real character, which atoms are, and in a theory of atomism are, then they have to keep added up. They have to have their symmetry and conservation laws, their invariance, what become continuity laws in terms of the transition of things and the conversion of things, here energy to other forms of energy, all in waves. But Zeno, it sometimes is said as like, well, he proved this, and then it's left to people to kind of strike their own path to arrive at, how there can be a smooth acceleration or smooth motion from left to right. Not as like, I go all the way there and count myself half back. I go all the way there and count myself half back. It's like, it's smooth. That Zeno, as well as Aristotle, both entertain the propositions that arrive at the infinitely divisible and the infinitely divided meet in the middle somehow, the middle of these two different developments, each from the same person. Zeno goes on. If more things than one exist, it is necessary for them to be as many as they are, and neither more nor fewer. But if there are as many as they are, they will be limited. If more things than one exist, the things which exist are limitless. For there are always others between the things which exist, and again others between them. And in this way, the things which exist are limitless. So we have the limitless, and then we have the notions of our limit. For having first shown that if what exists had no size, it would not exist, he continues. Yet, if it exists, it is necessary for each thing to have some bulk and size, and for one part of it to be a distance from the other. Now, this isn't so bad. This is still just this measure problem, and it's the measure theory. Because then, as soon as mathematics gets up into the measure theory and the continuous functions, pretty much for a continuous domain, then all sorts of developments live in the field. They don't. It's not worrisome. Which one of the ways these things is so, that it is so. So he describes. Zeno says that it is necessary for each thing to have some bulk and size, and for one part of it be a distance from the other. And the same argument applies to the protruding part. For that too will have a size, and part of it will protrude. Now it is all one to say this once and say it forever, for it will have no last part of a sort, and there's no longer one part in front of another. So this is forward induction, inductive inference. It goes on, and forever. The idea is that in the limit, sometimes there are the anti-inductive results, or non-inductive results. It's as simple that mathematics has points and lines. Whether or not they axiomatize it to exist, they have to still resolve that they do and don't, yet do. And then as for means, it's like then as finite beings, we only have our bookkeeping that can keep track of so many beings at once, and we'd lose track. But when you look at the very notion of numbering and say, for all the zeros and ones, the infinite sequences of them, in numbering, that there's no sequence that they don't make. Combinatorial explosion infinity. Then at the same time, when you have the counting argument, and say, when we try to count all these, there's one of them we don't count. The antidiagonal argument infinity. It's the same usual sort of thing. And when today we just have this notion whether it's points and lines that don't meet, or numbering and counting that don't meet, or some of these other notions, that they do. They're one for the other. Perhaps then, the translator reads, the argument from dichotomy comes from Zeno, as Alexander holds, but he is not doing away with the one, but rather with a plurality of things, by showing that those who hypothesize a plurality are committed to inconsistencies. Thus confirming Parmenides' argument that what exists is one. Simplicius. Aristotle discusses 4 of Zeno's arguments in the Physics, Metaphysica. Count and concise, and the text is in places uncertain. He says that Zeno argues fallaciously. For if, he says, everything is always at rest when it is in a space equal to itself, and if what is traveling is always in such a space at any instant, then the traveling arrow is motionless. Well, this isn't so unfamiliar as relativity and things living in their frame. This is false, for time is not composed of individual instants, nor is any other size. So that's fair to say that time is a continuous quantity, and that also there is an absolute, just like points and lines and numbers and counting, and absolute and relative, the global and total, and the point and local. They're all things. It's 0, 1, and infinity make the numbers. And matters of scale, matters of length, matters of proportion, matters of geometry and form, regularity, regularity, regularity again. Zeno's arguments about motion which embarrass those who try to resolve them are 4 in number. The first maintains that nothing moves because what is traveling must reach the halfway point before it reaches the end. We have discussed this earlier. The second is the so-called Achilles. This maintains that the slowest thing will never be caught when running by the fastest. The pursuer must first reach the point from which the pursuit set out, so that the slower must always be ahead of it. The same argument as the dichotomy, but it differs in that the additional sizes are not divided in half. Now, it follows from the argument that the slower is not caught, but it depends on the same assumption as the dichotomy. In both arguments, it follows that if you don't reach the end of the sizes, if the size is divided in a certain way. But here there is the additional point that not even the fastest runner in literary tradition will reach his goal when he pursues the slowest. The Achilles and the tortoise. Hence, the solution must also be the same. And it is false to claim that the one ahead is not caught. He is not caught while he is ahead, but nonetheless he is caught, provided you grant that they can cover a limited distance. Those then are the 2 of the arguments. The third is the one we have just stated, the fact that the traveling arrow stands still. It depends on the assumption that time is composed of instants, for if that is not granted, the inference will not go through. The inference will not go through. In a sense, they orbit the inferences. The fourth is the argument about the bodies moving in the stadium from opposite directions. An equal number pass an equal number. One group starts from the end of the stadium, the other from the middle, and they move at equal speed. He thinks it follows that half the time is equal to its double. Fallacy consists in claiming that objects of equal size move at equal speeds. The one past the moving object, the other past the stationary object, travel for an equal length of time, but this is false. Now that's a great thing, and it gets into a bunch of stuff. First of all, is that among the various continuous domains are these halving and doubling spaces. And this is kind of like, well, for the signal reals, there's this halving space. And in the line reals, there's this doubling space and doubling measure. And that ends up with a bunch of stuff in the Banach-Tarski or Vitali-Hausdorff theorem on the equidecomposability of a spherical ball into 4 or 5 pieces, which can be reassembled two in one and 2 or 3 in the other, and make identical copies of the same measure. That by dividing it, the Vitali's result that established the non-measurable set was, he said, I took 0 and 1, I split it up in infinitely small bits. Now they got 2 sides, ends up when I put them back together, it makes length 2. It's a doubling space or doubling measure. That's the whole reason that there's non-measurable sets at all, because otherwise he would introduce very directly this notion of doubling measure. Now, it's similar and shows up in a lot of different things, and with regards to the quadrature and the angular, because it's also for things like rolling wheels and the distance traveled by the axles vis-a-vis the distance covered by their circumferences, perimeters. This kind of notion of the Zeno's field argument and the back and forth thing is also like the distance traveled by the bee flying back and forth between two closing walls or something like that. Or there's lots of different things that help build up that it just kind of, it has a neat result. It's just that you just compute the time that it travels and the time that the one thing closes, and then what closes is in the same time. So there's the usual natural bookkeeping that otherwise you'd add up all the different distances and it would come out twice or half. So it helps reflect that bookkeeping is in effect, and it helps reflect that it's one of the richer than arguments and developments. And from reading this and hearing that there were these other 20 or 30 arguments of Zeno, if these very first ones are the very notions of what found our non-standard analysis and real analysis, one imagines that the other ones could have been simple or profound. So Aristotle says then that's the fourth argument. He says, for example, let the stationary bodies, equal bodies be A, let B be those beginning from the middle, equal in number and size to them, and let C be those beginning from the end, equal in number and size to them, and equal in speed to the B's. Follows that as they move past one another, the first B and the first C are at the end at the same time, and it follows that C has traveled past all of them, but B has passed half of them. Hence, the time is half, for each of the two is alongside, for each for an equal time. At the same time, it follows that the first B has traveled past all the C's, for the first C and the first B will be at opposite ends at the same time. C being, as he says, alongside each of the B's for a time equal to that, for which is alongside each of the A's, because both are alongside the A's for an equal time. So, that is the argument. It depends on the falsity we have mentioned. That's the most immediate thing that would otherwise contradict it. And that let out does not exist. Aristotle refers back to his early discussion on the first of Zeno's arguments. Traversing infinitely many things or limitless things, lengths and times, in general, all continua are said to be limitless in two ways, either by division or in respect of their extremities. So this is for this line reals and field reals, that the line reals is like, it goes between 0 and 1. That is its extent. And the field reals are all the fractions, the equivalence classes of all the ratios, so integers. So the line reals are just like, there's a numerator, it goes from 0 to infinity. The denominator is infinity. You got 0 over infinity to 1 over infinity, which is smaller than any regular real number, any member of the complete ordered field. It's an infinitesimal. But the only point is that it goes up to infinity over infinity, which equals 1. Standardly, it says the limit of these functions. It's just a continuum limit of the function. And it's formalized these days in this way. It's this way. And then the rational numbers is just being any integer fraction is like, well, you got 0 to infinity over each of 0 to infinity. So they fill out the space, and then they're infinitely divisible. You don't need real numbers to make the infinitely divisible. The rational numbers will do. Then that they are and that they're complete is the notion of their least upper bound existence axiomatized, because it's proven that irrational numbers exist. So they would otherwise have to be infinitely divisible. Then these signal reals are kind of as about that. It's like, well, once you fill all those out, and then if you had something that's just as fine of a comb over all the real numbers together, they each get half. Two further Zenonian arguments, and so sometimes you'll see Zeno spelled mostly Z-E-N-O, sometimes X-E-N-O-N, Zenon, Zeno or Zenon, Zeno. Are referred to by Aristotle. Sometimes you see Aristotle or Aristoteles, explained in more detail by Simplicius. It is clear that nothing can be in itself as its primary place. Zeno's puzzle that if places exist and they will be in something is not difficult to resolve, for nothing prevents the primary place of a thing from being in something else, not as in a place, but rather as health as in hot things, as a state of them, or heat in a body as a quality of it. So he's establishing that, well, we have these other means where we affect to reflect on complementary duals and mutually contradictory notions that we juxtapose in clear, natural as a square, an opposition in reflection. So in metaphor, when we have another one, we'll just relate it to that too. Zeno's arguments. Eudemus relates Zeno's opinion as follows. Zeno's puzzled. It seems to lead to the same conclusion, for he claims that everything which exists is somewhere, but if places are among the things which exist, where will they be? Surely in another place, and then in another, and so on. Against Zeno, we shall say that things are said to be somewhere in several ways. If he claims that whatever exists is in a place, then what he claims is not correct. For you would not say that health or courage or 1,000 other things were in a place. But if somewhere is taken in another way, then places may be somewhere, for the limit of body is somewhere in the body, namely at its extremity. Eudemus, Physics Fragment. Simplicius. Zeno's argument that any part of a millet seed makes a sound. Tell me, Protagoras. This we read last time. So Zeno is pretty great. And to him is assigned the classical exposition of classical motion and time. And the notions of the infinitely divisible, the bookkeeping, the whole and the parts which come together and keep measure in time, and the various thought experiments surrounding that, when it results that mathematically what lets out is also the doubling spaces and halving spaces. And exactly. Mechanics is having that as its mathematics. So, and then that gets into how and why there is to be figured out, and it's kind of addressed in some of these notions of when something topples, and it goes from being a singularity in one dimension to the tangent in another one, with regards to notions from the integral analysis, the tangent and subtangent of the ordinates and abscisses, all the way back to this identity dimension bit for the stop derivative bit, and for things like the radial basis function and the Dirac's unit impulse function. The first and only greatest non-standard function is Dirac's unit impulse function. It's an infinite spike at 0. It's infinitesimally wide, yet its real analytical character has that the area underneath it equals 1. Now, there's a version of it where it equals 2, and there's a version of it where it equals 1/2. They're different ones, according to this halving and doubling space. But the first and only non-standard function that anybody knows is Dirac's unit impulse function, Dirac's delta. So, well, that's kind of what there is of that for the moment. Here's a book. And what it is from classical to quantum mechanics. And so it helps to, I imagine, affect to relay the ideas of what is the quantum, what is the point particle, what is the atomic, what does it really mean that there's an Avogadro's number of atoms in a mole of atoms, that stoichiometry in perfect proportions of elementary Democritan chemical elements are so perfect in the theory. Democritus, for the Democritan being the theorist to who's attached the idea of the atomism and the subatomic and the elementarily constituent, which for some deconstructive account makes for how it is the atoms, the indivisible, atomos, uncuttable, are matter-of-factly reflecting as much just that they're in the nature of the continuum mechanics, where it so reflects that it's a potential, practical, or effective, or actual infinity. So, this book by Giampero Esposito, Giuseppe Marmo, and George Sudarshan from Cambridge University Press carries on this way. INFN, Stagione di Napoli, and Dipartimento di Scienze Fisiche, University Federico II di Napoli, and Department of Physics, University of Texas, Austin. An Introduction to the Formalism, Foundations, and Applications, 2004. The Need for a Quantum Theory, Our Path Towards Quantum Theory, the Photoelectric Effect. So, after Compton and Millikan oil drop experiment, atoms were discovered. The electron was, in this sense, assigned value. Electron physics so resulted. Particles are waves. Waves make particles. Particles are an idea. They're theoretical particles. The photoelectric effect and the relation of photons and electrons by their energy, and then there is discrete. Then a lot gets into the electrons as discrete according to orbitals, and this was discussed quite a while back, pretty thoroughly. And there is something to be said, though, that even in the modern theory, as the elements get larger, then it so results that the orbitals, and then as for their lobes and such, and the angles of bonds, which do affect to reflect the density of and material properties of matter in its elementary form, according to the nuclear model of physics and atomic chemistry, then makes for molecular chemistry that there are that is non-local, and then it also has that there are notions that the discrete is it's so exact, does let out that for the spectroscopy and lines, there are yet the spectra. That for for current and that it is of that the physics of this is again continuous. So that gets into current and historical models of the atom and of the nucleus and these things, given the incredible success in particle physics and quantum mechanics, which is never wrong. Compton effect, interference experiments, atomic spectra and the Bohr hypothesis, the experiment of Franck and Hertz, wave-like behavior in the Bragg experiment, the experiment of Davison and Germer, position and velocity of an electron, problems. Phase 1 form, classical dynamics, Poisson brackets, symplectic geometry, generating functions of canonical transformations, Hamilton and Hamilton-Jacobi equations. See, only 20 years after the Scheveningen conference, where this was just coming up, it's like it's a textbook. The Hamilton principal function, the characteristic function, Hamilton equations associated with metric tensors, introduction to geometrical optics. Now that I'll be interested in, because optics is geometrical optics is kind of combining two things, because the optical is the effects in diffraction, whereas the geometric is that light goes in a straight line, and for all matters of range finding and such, it's that's how it is so. Vis-a-vis the geometric character of light and the optical character of light are two different things. Vis-a-vis geometric optics, optical geometry, vector fields, wave equations, Cauchy problem for the wave equation, fundamental solutions, symmetries of wave equations, wave packets, Fourier analysis and dispersion relations, geometrical optics from the wave equation, phase and group velocity, the Helmholtz equation, aeconal, it's a name, I imagine, approximation for the scalar wave equation, wave mechanics, from classical to wave mechanics, uncertainty relations for position and momentum. Here there's discussed, Heisenberg's certainty principle and these kinds of things. Green kernel of the Schrodinger equation, that and the Schrodinger's cat's tape recorder. JWKV solutions of the Schrodinger equation. From wave mechanics to Bohr-Sommerfeld. Applications of wave mechanics. Reflection and transmission, step-like potential, tunneling effect, linear potential. Schrodinger equation and central potential. Hydrogen atom. Introduction to angular momentum. Spin numbers, spin, angular momentum. This is also, there's the Dirac positronic sea, the particles and antiparticles in a vacuum, ever empty, of them. Similarly, Einstein's white holes everywhere, a place and a fixture in the spatial and the space everywhere. For moments, angular moments, which essentially results that matter sort of is. Gets up into scattering and tunneling theory. Part 2, while quantization and algebraic methods. The basic postulates of quantum theory. Landau levels. 2 photon coherent states. Klebsch-Gordon and the Regge map. So Regge, R-A-G-G-I, has got a lot going on with regards to adding the things together and keeping them up together, kind of like the Ricci tensor and the Regge map. Monopole harmonics. Eigenvalue problems. From classical to quantum statistical mechanics. Aims and main assumptions. Partition function. Getting into bosons and fermions, and otherwise pair statistics, and those which obey neither, and how those are all somehow probabilities, and non-standard probabilities, because in the quantum model, according to Copenhagen interpretation, they're quantum probabilities. The Dirac equation. The Kirchhoff principle, antiparticles, and QFT, quantum field theory. So in quantum field theory, it's like, well, all we have is particles and all we have is quantum amplitudes, but the field is all around, and so it's sum of histories and sum of potentials. So our sum of histories is arrived at a quantum state, and the sum of potentials is all around. Quantum field theory, it's continuum mechanics again. Points and lines, and lines and points, they can't make each other. They do. This deserves great attention and a thorough and extended study, and is the contents of a course to arrive at this a sufficient level of knowledge to be able to work out a lot of these different kinds of things. I'll put it here next to the study on the path integrals and the quantum processes, which helps explain effect to relay that the path integral is mostly classical. Then there's a couple different places where it's like, well, we have a half here or two. It's kind of gratuitously, because of Zeno. We might as well call it Zeno's half. So moment motion, we're still trying to figure out classical mechanics. And then here I'm going to pick up from d'Espagnat where we left off and see what insight he provides in his inspiration. One of them consists in the pair of concepts molecular structure versus temperature. Starting from indivisible quantum endophysical reality, we arrive at an exophysical description in terms of molecules by performing one given abstraction. And we arrive at an exophysical description in terms of temperatures by performing another abstraction incompatible with the first one, so that neither one of these two descriptions is more basic than the other one. Same thing with numbers and counting, or points and lines, points and spaces. 0, 1, and infinity, it's kind of like geometry. It's like skip lines, just go from points to all the space. Skip the rest of the numbers, just go from 0 to 1 to infinity. And here for temperature and the macromolecule, it's like, well, there's heat and there's substance, you know. In the inductive course, then you make usual counting arguments and things that add up. It's required to have an inductive course for these things. And so the very notion of the non-standard or the superclassical is how it works out besides. How it works out in the deductive about, like, this is how all the ways that it could arrived at that they even out, that they make each other in a symmetry of some sorts and form. Here that's addressed with regards to these halving and doubling spaces. And then about the counter space of all the zeros and ones, the sequences of zeros and ones. And then the one argument from counting it up and adding it up ends up being A, uncountable, and B, not really having any way to assign an analytical character or topology. And another way to look at it is like, hey, each of these columns is half zeros and half ones. Bookkeeping somehow makes it so. So it arrives at a lot of different things that would otherwise have no convergence criteria at all. From one perspective, have that behind that point in infinity is another one. Behind the speed of sound is the speed of light, and behind the speed of light is CG, when CG is Newtonian or infinity. In perspective and projection, they're all the same point. But according to the parallax and peripheral parallax, they keep their greater context. So I really enjoyed this last quote from d'Espagnat here about the exophysical, endophysical, and in terms of just saying, hey, we got atoms, but as soon as you start looking at molecules versus temperature, one or the other's got to give. And they do. They give to each other. That's how it goes. All throughout our study, we shall, in this or other forms, meet with what constitutes the gist of these ideas, namely the fact that unquestionably some reality exists on its own, but that it shows itself to us in forms depending a lot on ourselves and the abstractions we perform. Chapter 6. Universal laws and the reality question. The reality, in quotes. Reality. 6-1, the theoretical framework notion. What is it that makes some developments in physics manifestly much more significant than others? On pondering this question, I, for one, came to consider that in pure physics there are, in fact, two kinds of theories. Those that deserve the name theoretical framework, and those that we may call theories of the ordinary sense of the term. A glance at the history of science immediately clarifies the nature and the motivation of this distinction, for in it we find an elementary, clear-cut instance of a case in which it applies, and consists of the two most famous Newton discoveries, Newtonian mechanics and universal gravity. For indeed, the first one is a nearly perfect example of a theoretical framework. By this I mean that the three Newton laws constituting the said mechanics are statements considered fully general, applying to all conceivable situations, but correlatively not including the detailed information needed for quantitatively predicting any phenomena whatsoever. In particular, they do not stipulate the law of forces, or the laws of large numbers. In contrast, the gravitational law is an example of what, for lack of a better term, I just termed theories in the ordinary sense of the term. Such a theory should be specific enough to enable the physicist to determine at least the main lines of a set of phenomena. Newton's gravitation theory does this by specifying the precise nature of the law of forces. So we spent a lot of time here talking about Newton and the giants whose shoulders he's standing on, and when they came up with all this stuff, in terms of the system of the world and the laws of motion and this kind of thing, what he was able to synthesize and simplify and make a severe abstraction. And then here it's that force in kind of forces live in a field theory, and the field theory has forces. These are its points and lines. These are its points and spaces. These are its absolute and relative, and these are its potentials and real, classical. The idea is that the reality is a sum of histories, sum of potentials. By definition, it just kind of is. And then that the linear impulses and moments of the classical theories are having terms that are so simply algebraic with respect to each other that to add them all up results is about how they are, again, just part of the sum of histories and sum of potentials also. And in fact, it's not so much that it adds up to the other things as the other things add up to it. So mutually. Well, that's all for today. I shall wish you a good day.